Welcome to the European Synchrotron, the SRF. We're now going to enter in the central building, and then we are going to approach the experimental hall and see the upside of the tunnel. On the mezzanine of the central building, you can see here a maquette of the SRF synchrotron, and here a maquette showing the outline of a beamline with the accelerator, storage ring, and the beamline. Here is the accelerator, and here is the X-ray beamline with the optic hatch, and then the sample area where the data acquisition is done, and then the control room. And now we're going to approach the experimental hall. So all the way here is full of posters explaining all the different applications you can do of synchrotron, on material science, earth science, climate, all cultural heritage, energy, health, innovation and biology. And then we enter the mezzanine and the passerelle to go in the experimental hall. Here we are in the experimental hall. As you can see, all the different infrastructure of the various beamlines. But in particular, I would like to show you the rooftop of the tunnel. Under this concrete roof you can find the storage ring with the electron accelerator, the EBS that has been presented by Harold today. And on this line you can see basically the trace of the electron beam. Here you can see a bending magnet when we have the change in direction, and normally the light generated by that bending magnet is going to be collected by this beamline here, BM01. So now that you have seen the source from where the X-rays are coming from, you can see all the X-rays are collected into pipes like this one and transferred from the accelerator storage ring to the different experimental hatches. Experimental hatches that from the top looks a bit like this one. You have many experimental hatches all adjacent one to each other to collect the X-ray beam and run the experiments. And here we can see some of the elements which were in the storage ring of the previous SRF machine. Now this piece is has been substituted by the EBS, the much more complex design. We can see a succession of quadrupole and hexapole that were basically the elements, the focusing elements, or the elements that are supposed to condensate the electron beam in order to reduce as much as possible its size, and then increase the brilliance. So you can see here how the elements look like, but in particular you can see the undulator, which was the element that successfully was implemented at the SRF when the first third generation machine was put in place. We can see the vacuum chamber, very simple design, much more complicated than one of EBS today, which you can see where the electrons are flowing, and then we can see the different magnets that are responsible for the driving of the electrons and then the generation of lights. Now we are going to go together on the beamline ID31. A beamline has been recently built in the context of the first phase of the upgrade of the SRF. ID31 is a high energy beamline, which the characteristics of being capable to have be very versatile. A lot of different experiments are possible there, and to be capable to have very high energies, and in particular very high, very big, heavy samples. Hello, Jacob.
Hello, Enyo.
Thank you very much to host us here on your beamline on ID31. We're very happy to have the possibility to see the instrument also, if with this sanitary crisis was not possible to be here in person. So Jacob, if you can just show us a bit about this instrument, which is quite unique actually and quite new here at the SRF. So tell us a bit more.
So I'm Jakub Drnek, I'm beamline scientist here. So I'm a physical chemist actually. So it is quite a unique instrument. So this is very high X-ray energy instrument that we typically work at energies between 40 and 100 kiloelectron volts. And the idea here of this beamline is to look at various materials, how they actually work in their native environment or during the operation. So one of the big theme here is, for example, the research of materials for energy applications, like in batteries and in fuel cells, and materials for hydrogen storage, for hydrogen economy. And what we typically do is we take those materials, we put them into the real battery, and then we charge and discharge the battery. We just, let's say, run the battery as it's in the car, and then we look what's changing inside the battery. And for this we need those high energy X-rays, because we have to penetrate all the housing, everything which is outside, to see actually inside. And the X-rays, high energy X-rays, are excellent. So how we typically do it, so we can go in, we're at the beamline. So here we're stepping in. Now, because it's a high energy beamline, we have these very thick lead doors, which are very heavy. You know, I have to use like 2 hands to stop it when it goes. Right, and that's because the radiation is high energy, so it's penetrating. So that means we have to have quite a thick lead wall, so it does not irradiate us during the experiment. So here we step into the beamline, into the experimental hatch. then you can see what we see right now. So we have this karna, which we call, this is this large granite piece where it sits the detector. We're gonna see the detector a little bit after, right? And this detector can move back and forth pretty much in any position of in the hatch. And that's very convenient, because what we do is elastic scattering, so X-ray diffraction and small angle scattering, or some kind of imaging. And for this, we need to really position the detector at different parts of the reciprocal space, so at different positions in the hatch. So you saw before that we have two detectors here, which are very far away from the sample here. So this detector we use for small angle scattering, and this is our imaging detector. We just use to do simple tomography. Then we have a large fly tube. So this is evacuated fly tube here, where the X-ray goes. So we don't see the scattering from the air. Right? And this is why the hatch is so long, because we have to measure far away, but if you measure far away, you need to make sure that you don't have the background from the air scattering. And then you have the fly tube. And here is our experimental station. So for this experiment, there is a capillary sample. This is a catalysis. This is a catalyst which sits in the capillary. Then we heat up the capillary with those two things, which are just gas blowers. So they are like your typical fan in your bathroom, right? So we heat it up to about 800 degrees Celsius. And then we study, we're gonna move the detector about here, right? And we study what's happening with the materials as it undergoes, as it goes to catalysis. So this is, so this is the detector. So that's where we catch the images, and that's the most expensive piece of equipment on this beamline, is the detector.
How much?
How much? So the detector costs about €1 million.
Wow.
You can buy like 10 Ferraris for that. For such a little box.
That is much faster than a Ferrari, isn't it?
That's much faster than Ferrari, yes. At the end. It's much more complicated technology than Ferrari. Okay, so of course we have to have all the auxiliary things here. We have two stations, so now we are looking at the station, which we put like heavy batteries, heavy equipment, lasers for let's say if we do additive manufacturing, so 3D printing setups we put on this station. And this is what we call the other station. This is what we call our micro station, which is very fine movements. So we use it typically with very small beams, which our beam can go to only a few microns in size. And this setup moves conveniently within that range, right? Very reproducible. So it's a special setup. You see the hexapod here. This is how you position the sample. You can move it up and down, and you can move back and forth, and left and right, and so on. The beam comes from this tube, right? So we also need to cut the scattering from the air of the incoming beam, and then in the hits you don't see it. Behind the gas blower is the sample.
So Jakub, the people that are going to see this video is from the conference vvwam workshop on additive manufacturing. So they're going to be very, very interesting about what we do with metallurgy. So you say high energy beamline. This means for me that is the ideal for metallurgy. So how high is high, and basically this is the stage that they're supposed to use if they want to do some in situ experiments.
Exactly, right? So we have experiments which typically people bring the lasers, they heat up the powder, right? And they look as they just raster the laser through the powder, for example, bed. So they look how the powder solidifies melts into the actual 3D print. Because that's of course very important
Application.
question, right? As probably everyone from the conference knows. so that's it. So we are very set up for this kind of experiment. We are one of the few beamlines who does actually additive manufacturing at this area. So you are
That's
welcome
great.
to come, that's for sure. And your experiment, they're ready for you.
Thank you very much. That's
You're
great.
welcome.
So we look forward to see more of in situ additive manufacturing on your beamline. Cheers.
Goodbye.